Okay. All right. Hi, everybody. I'm so glad that you could tune in today to learn a little bit about a very interesting cell signaling pathway. Today, I will be discussing apoptosis, which is also known as programmed cell death or cell suicide. Okay. So let's begin. What is apoptosis? As I said before, apoptosis is cell suicide. It is programmed cell death. For me, it's very helpful to look into the etymology of a word. So if we look at apoptosis, it comes from the Greek apoptosis of falling, from the apo or ptosis, from the falling off. So altogether, apoptosis literally means falling off of. And I really think that that's very fitting, and it was very helpful when I was trying to understand what apoptosis really was. And this was really helpful to look at the falling of leaves in autumn. So when the leaves fall in September and October, it's considered very natural, cyclical. It's a fitting process for the season. That is very much the case for apoptosis. Apoptosis is a very natural and necessary function in all of our bodies, and it's constantly happening. It's happening right now in everyone. Let's begin with talking about the causes of programmed cell death in general. The major ones are embryo development, DNA damage, infection, and environmental stress. All of these except for embryo development, which I'll touch on a little bit later, I will talk about momentarily. When a cell becomes damaged, infected, or stressed, the body needs to rid of the cell before it affects any of its surrounding ones. And that's where programmed cell death comes in, and that's where the core of apoptosis is essential. So beginning with some of apoptosis's major goals or purposes, specifically for apoptosis and not general programmed cell death. The first is equilibrium, then we have cancer prevention, and then we have immune system function. So let's begin with what I mean by saying equilibrium. It may help to consider the fact that most cells, well, every cell in our body, has a shelf life, so to speak. For example, the average red blood cell has a shelf life of 120 days. At the 120-day mark, apoptosis is scheduled to occur. If a cell lives longer than it should, that is when horrible diseases like cancer occur. Cancer is often an abundance of unwanted cells, and when apoptosis does not kill the cells efficiently enough, that's when it can happen. Preventing cancer-causing cells is what gives apoptosis its protective role over the body, and it's what helps the body stay healthy. Apoptosis in this respect, it ensures that the cell's circle of life is carried through on schedule. So in this diagram right here, we can see what I was talking about with cancer prevention. We have on top an unfixable cell with severe DNA damage. It could take one of two routes. If it takes the left, if it goes with apoptosis, there's no risk for cancer because the cell is destroyed, it was neatly carried away, and it will not affect its surrounding cells. Whereas on the right, the cell will continue to divide, the cell will continue to affect other cells around it, and this could potentially lead to cancer. Okay. The other main type of cell death is by necrosis. These two concepts are very, very often mixed up, and I'm here to differentiate between the two and ensure that you never make the same mistake. Firstly, there are major differences in the cell's structural changes when undergoing necrosis versus apoptosis. Necrosis is often known as the messy cell death. During necrosis, the overall integrity and shape of the cell is entirely lost. The content of the cell will swell and eventually explode. Then the cell's contents will scramble and disarray and so disrupt surrounding cells. This is why necrosis is very bad. We don't want necrotic cells. It can lead to severe health conditions due to its major inflammatory reaction. When the cell explodes, it contaminates its other cells, spreading diseases or cancer. Apoptosis, on the other hand, is the neat cell death. And apoptosis, instead of exploding, first expanding and exploding, the cell will shrink. The shrinkage will cause the cell's content to clump together, and this can be described by a very fun term, in my opinion, called blebbing. Blebbing is a scientific term. It is a term for when the content of the cell clumps in different sections and disperses in a very tidy fashion. In addition to this containment, another reason that apoptosis does not customarily affect surrounding cells is because the blebs will be recognized by your body's immune system, and in turn, immune cells absorb the damage. It will absorb the dead cells before it can affect any other cells. I like to imagine it as a vacuum. You can think of necrosis as a ground full of scattered, crushed, pulverized crumbs, whereas apoptosis is a ground of whole crumbs. So still bad, but more manageable. It isn't a powder, and the key difference is that not only will the powdered crumbs of necrosis get stuck in the carpet and leave stains maybe, you never know, but also that the apoptosis crumb scenario, there's a giant all-absorbing vacuum which cleans the carpet, sucks in all the dead crumb cells. In addition to the structural differences, there is also a difference in the timing of necrosis versus apoptosis. As we saw earlier when discussing the etymology of apoptosis, there is a very natural and cyclical nature of it. It is very controlled, it's a process. There are several steps ensuring the timing. And that is also why the consequences of mistimed apoptosis are so severe. Late apoptosis can result in cancer, while apoptosis occurring too frequently and so killing cells more quickly than necessary can result in diseases like AIDS, heart disease, liver disease, amongst others. Necrosis, on the other hand, is very random. It's uncontrolled, it's messy. Necrosis will occur wherever, whenever the cell is under incredible duress and stress. It is an unregulated and a process, and it's almost like hitting a very, very dangerous panic self-destruct button that you're never, ever, ever supposed to press. Okay, so if we wanted to put a visual to what I was talking about earlier, the messy versus neat, we have on the left necrosis, and you can see the content of the cell being scattered all together. Whereas on the right, apoptosis, it blebs. It's very controlled. It's contained. You have almost vesicle-like things occurring. And another visual is apoptosis. You can see the shrinkage in this. So to make it more visual, you have the normal cell, then you have the condensation where the cell itself will shrink, all the contents will shrink as well. It will fragment, and then the apoptic bodies will also disperse very neatly. Great. So now let's talk about the apoptosis pathway itself. To break down this rather complicated pathway, we'll talk about it by its two types, intrinsic and extrinsic. So if we begin with intrinsic, I wanted to first show you this diagram of an intrinsic pathway. Wow, I know, it looks very complex, and I just wanted to show you this to expose you to the complexities of this pathway. We are not going to go into great depth in this pathway, but I also thought that you should acknowledge the fact that there are many steps, and we're only looking at the core steps today, which will give you the main ideas. And the core steps itself is that we have activators and inhibitors. So on the left, we have anti-apoptosis, and on the right, we have apoptosis. You can see the activators and the inhibitors. I'll explain that in a second. So first, we have the inhibitors. We have BCL2 and BCXL. Then we have the activators, which are proteins. They are BAX and BAK. I like to think about this in a way of scales, so I diagrammed two scales for you right here. First, we'll talk about the pro-apoptosis scale. There are 3 steps in this scale, and you can see that in this scale, the activators are majority, and so the scale's leaning toward the activators, and therefore apoptosis will occur. It will begin with BAX or BAK activating cytochrome C. When cytochrome C is released, it will activate caspases. What I really need you to know about caspases is that wherever there are caspases, there's most likely cell death. This is a very important concept in all that we'll talk about in the future. On the direct opposite, we have a scale where the inhibitors are majority, and so it's leaning toward the left. It's leaning toward no apoptosis. In this case, there aren't enough activators that your body will say, okay, it's time for apoptosis. And this, because there aren't that many activators, cytochrome C has no way of becoming activated. This is a chain reaction. Caspases won't be activated, and as we know, no caspases, no cell death. This will result in uncontrolled cell survival, and so cancer. Okay, now we are going to talk about the extrinsic pathway. So I thought it'd be helpful to talk about how the extrinsic pathway begins because there are really three instances in which it could occur. The first is that we have a TNF alpha binding to a TNF receptor. You can see that on the right. The second is that a fast ligand can bind to a fast receptor, which is directly below. And the third is that a cytotoxic T cell will be present. In the first two instances, after a ligand or an alpha binds to its receptor, the transduction will result in initiated caspase. Bottom line in these instances is that wherever there are caspases present, cell death will occur. The maybe more interesting, more fun occurrence is where there's a cytotoxic T cell. So whenever the cytotoxic T cell is present, it will have many steps. And this is what we also call a cascade because it isn't just one call and response action. It's call, response, etc. So first we'll have a cytotoxic T cell present. Second, that T cell will initiate a granzyme B molecule. The granzyme B molecule will then contact perforin, and then the perforin will enter the cell and activate caspases. As we know, activated caspases results in apoptosis. In this example, you can very clearly see the difference between the intrinsic and the extrinsic pathway. It's almost very self-explanatory, but to put it in very clear terms, as you saw in the cytotoxic T cell example, the apoptosis itself begins outside of the cell. All extrinsic forms will begin outside the cell, whereas the intrinsic pathway begins on the inside, corely in the mitochondria. Great. So now that we understand the basics of the apoptosis pathway, we should discuss the more ominous occurrences where apoptosis goes wrong. Obviously, we have already seen that when apoptosis does not occur as regularly or effectively as it needs to, this results in excess cells or cancer. One specific cancer, which is a direct result of excess cells, and I thought it would interest you all to know, is follicular lymphoma. You might have heard of it. More specifically, when apoptosis does not occur, it allows for a very unstable environment where gene mutations can form and thrive, where cells will not be as protected from immune destruction, and on a larger scale, where the cell cycle itself is completely thrown off because cells are no longer checked and therefore can continue to grow and feed off of things like growth hormones. In the biological realm, this is called carcinogenesis. It's defined below, and you can see it's literally the initiation of cancer formation. A carcinogenic environment will occur due to inappropriate cell growth and unchecked hazardous mutations. On the opposite end, as we softly touched on earlier, there are also physiological consequences that result from an overabundance of apoptosis. Some of these include earlier mentioned AIDS, heart disease, and liver disease. Great, so we've gotten through the main chunk that I wanted to today, and I thought it would be very helpful to look through some really amazing real-life examples of apoptosis on a non-molecular level. So first we have a photo of a mouse embryo at 15 days old. And we can see that the foot, it is a foot, it's not fully done forming. And so you still see the web-like areas between the digits. And this shows that apoptosis is responsible for digit formation. Before our hands and feet were molded into what we see them as with individual fingers and toes, apoptosis has to kill the cells of the web-like material between the fingers. Okay, so here's another diagram that I thought would be helpful of a mouse paw, and it is an embryo at day 12.5. So you can see it's a big clump, like our hands don't look like that. Whereas on the right, after just one day later, you can see very clearly the digits beginning to form, and the red dots show cells that are currently undergoing apoptosis. Great. The next example is the transformation of a tadpole to a frog. We all hopefully know that frogs don't noticeably have tails, but tadpoles too. So I was very interested to know as to why that was the case, and Remarkably, apoptosis is responsible. So you can see on the left that a tadpole does have a tail, and it must first undergo apoptosis before it can become the adult frog you see on the right. So the genetic material in the tail of the tadpole will be resorbed and it will be killed by apoptosis, and that's what results in the frog on the right. Okay, that's all that I have for you today. I really hope that you enjoyed this segment on apoptosis and that you are interested enough to watch some more videos about the true complexities of the pathways. But for now, I hope you all have a wonderful rest of your day, and I'll see you all later.